All right. So over here we have Recitation 8 and we have problem 1, and it says that we have a rigid tank that initially has 7 kilograms of mass as a saturated water vapor. Okay? And it starts at 100 degrees Celsius, and the water is then cooled to an ambient temperature to 25 degrees Celsius. Okay? So we don't have any boundary work because it's a rigid tank, and this is the mass, and it's a saturated vapor that's from the tables, and this is T1, and this is T2, and because temperature is decreasing, we know that there is Q out, okay? And now it says to sketch the process of TV diagram, including all the T and V values, and the ISO bars with the corresponding values, okay? So from our schematic, we have a rigid tank, okay? And since there's no work, we're not going to include that, and there's no mass flow because it's a closed system. And so we're just going to add our Q out, okay? That's for our schematic for now. And for a TV diagram, here we have. So since we're starting at a saturated vapor, we can just assume that we're on this line, wherever on this line, doesn't matter. And then we're just going down to another spot. Let me just move this a bit like this. And we're moving to another spot inside because it's the same volume. Because it's the same specific volume. So specific volume 1 equals specific volume 2 because it's a rigid tank. So our volumes are equal and our mass is equal because it's a closed system. So since both of these are satisfied, this is satisfied. Okay? So that means that we just go straight down, and this is state 2, this is state 1. And now we look at the property tables for our temperatures, and we have, so this is the water depending on temperature, saturated water. So we set 100, okay, and then we set 25. Since we're out of vapor, we say it's 1.7672. 1.672. So this is our value, so 1.672 millimeters per kilogram, and then this is 100 degrees Celsius, and then this is 25. And since they're both saturated vapors and they're in the dome, we can just find the pressure values. So this is the pressure value for the second one. So 3.1698. And we have 101.42. So we draw our isobars. And that this should be our TV diagram, our full TV diagram. And now it says determine the entropy change for the water in kilojoules per kilogram, and has entropy increased or decreased. Okay, so our entropy change is going to be, our formula is going to be, let me color this different. So change in S equals to S2 minus S1, which also, we don't know the real value, so we're just going to take it mass times the specific entropies, and we can find our specific entropy from the table. So we have 7 kilograms of mass times S2 minus S1, and S1 is just 7 point, so 7.3542. And to find S2, we can just find the quality because we have the volume. So we say the volume minus volume of liquid over volume of change in volume equals to our quality. And we should get from the tables. So we have these, and plugging that in, 1.2 our quality should be, so let me write the values. Uh, let's say 6 because it's 5, 5. Okay, and we can just find now we can find the S2 equals to SFG times X plus SFF, and we can just find that from the tables. So it's this, and that would be 0.386 times, let me treat it like this, and then it's 8.1895 plus, and that would equal to 0.6833 kilojoules per kilogram Kelvin. Okay, so plugging that back in, so this should be here, and that should be 0.6833 minus 7.3542 times 7 should be equal to negative 46.7 kilojoules per Kelvin. So, going back to the question, we say our entropy has decreased because our S2 is lower. And then for the water, it's surrounding determining the entropy generated. So, entropy generated, we have an equation for delta S. So this is the entropy balance equation, equals to ms minus sum of this in, this out, m of s plus sum of in of kq tq minus over tk, sum out plus s gen. Okay, so there's no mass flow because it's a closed system. These are cancelled, and we don't have any q in, so this is cancelled. And we just need, so this is q out, and we'd say that we'd cancel this because it's only one outlet. Okay, so our value of negative 46.7 equals to our q out over the temperature in Kelvin. So our temperature at the going out is going to be 25 because it's the ambient pressure. So 25 plus 273 is 298 plus S gen. Okay, we don't have Q out, but we can find it from the energy balance equation. So we have, let me write on the other page. So delta U plus delta KE. So there's no mass flowing, so that we cancel that out. We have no work, we cancel these out, and we don't have any Q in, we cancel that out. And it's stationary, so we cancel this. So we have mass times U2 minus U1, and then it equals to negative Q out. And from that, we can find from the tables that this is 250x. And from our quality, we can find x UFG plus U of F equals to U2. And that would be, so let me just write that down. So what was the value? 0.386. Oh, it's 0.08. 386. Let me fix this. Did I get that wrong? Yeah, I just missed the zero, sorry. And, okay, so 0.086 times our 23, 4.3 plus 104.83. And, okay, so now let's calculate this. Yeah, so you should get 193.78 kilojoules per kilogram. So now getting the change, so our, so this should be 193.78 minus 2506 times 7, and it equals to, and you'd get 161.85.54 kilojoules per kilogram. So this is our value for Q out. So plugging it back into this equation, so we get 161.85.54 8 negative to negative 46.7 plus S gen. Okay, 46.7. And our S gen value should be 7.6 kilojoules per kilogram. Kelvin? I mean, kilojoules per Kelvin. Okay. And now we want to redraw everything and put it in a TS diagram. Okay. So our temperature 1. So we know this still. Okay. But we don't know where our S value is. So our S value should be, so S2 and S1, we have those values. So it's 7.3542 from the table. And we calculate this one, so it's 0.6833. Okay. And still a mixture, so let's just put this as 7.3542, 0.6833. So this is our top. 100, 25. And then our pressures are the same as before. This is 101.482. And this is 3.1698 kPa. Okay. So there's all they do also over here. They have some other lines for the specific volume. These are isochoric lines. Uh, I wouldn't always draw them. Only draw them when when you know it's, or it is isochoric. Never mind. So you only draw them when your system or like your change is isochoric. So it is. So when you do, it's just you add another line. and they peak at it like higher, like their slope is higher than the isobars, and then just like tilts down like this. It never reaches the line, and then just say the specific volume equals to 1.672, was it? Yeah, 72 meters cubed per kilogram. Yeah, but usually don't want to always add them because it causes clutter and it's really hard to tell. But yeah, and that's all for question one. And question two, we have an insulated, so there's no Q, and this is our volume, and saturated refrigerant vapor of R134A, initially measured at zero point 0.8 megapascals, and is allowed to equilibrium with the surrounding and with a reversible manner. So this is reversible. There is no S gen. And the surrounding atmosphere is at. So this is P2. This is P1. Okay. Okay. Since it's a piston, we know our volume is changing. So let's look at the tables and go to R134. So here are where are these are the pressure tables. So it's 0.8 kPa, so it's 800, and we have 400. Okay. So our temperatures. This is T2. This is T1 because we're gonna need it for the TS diagrams. So we have, and then we have 8.91. Yes. Celsius, and this is, let's do it on the same line. So 800 kPa, and then this is 400 kPa. And let's draw our dots. No, it's here. It's here. Uh, since it's for this, we have an energy balance for, or the entropy balance. So S goes to S plus or minus out of an S. Okay, since it's reversible, we we take care of Sgen, and it's a closed system, so we take care of these with the mass, and then we have to take out these two because it is insulated, so everything over here would equal to 0. So we're saying S1 equals to S2. Same with the specifics because the mass is the same. So for our TS diagram, we know that it just is a straight line down. Okay, and we can just label our pressures to be equal. So this is 0.8 megapascal, 0.4 megapascal. This is D1, this is D2. Okay, so we can find our value for S1, or specific one. So the specific one equals to our value, so it is vapor, so it's 0.98. So we have 0.91853 S2, which equals to 0.91853 kilojoules per kilogram Kelvin. Okay, so now we can find the quality, and we can find, so the quality S2 minus S of F over S of G. And we should find that for our equality for the second state. So we have this minus 0.24757. Let me write that down. 0.987. Okay. And to find our specific volume, we just do x f b of f, which equals to, from the tables, 0.051266 minus 0.000790 plus 0.007905. Okay, so that should be 0.05063. That is for V2. V1 equals to, let me see, 0.025645. So I know V2 is larger than V1, so we just do it like this. I just want to signal it like this because it's all under the dome, not going out of the dome. So this is 1, 2. This is V1, V2. I don't know if it's accurate. Okay. Okay. And okay. So this is, we sketch these and then determine the final temperature of the refrigerant, which we just said that is 8.91, and calculate the boundary work associated with this process. So we know there's boundary work because the volume is changing, but we don't know if it's on or by the refrigerant, so we can't really draw it on the schematic yet because we don't know the direction. We have to calculate the energy balance and see where that tells us. So delta U in Q in minus Q out plus work in work out, and then plus. So it's a closed system. We don't have this. It's adiabatic or insulated, so there's not that. And it's stationary, so we don't have this. And we want to find, so we have, do you have the mass? We don't have the mass. We calculate the mass by just doing uh, from the specific volume. So we have over specific equals to the mass and equals to 0.14 over 0.025645 V1, and that would give us 0.025645. So it's 5.46 kilograms. So now we just do M of U2 minus U1 equals to either work in or work out. Or let's say work net, because we don't know if it goes in or out yet. So we have to calculate our U2 because we have everything else. So this is 5.46, and then we have it as U2 minus U1, and U1 is, let's see, vapor 246.82. Or am I getting this wrong? Yes. So 246.82. And from the quality, we have it as 0.987 times UG 171.49, 171.49 plus 63.61. And that would get, so let's just write it down. Of 171.49 plus 63.61, and that equals to 232.87. And that would all just give us negative 76.16. So it's negative, so it's worked out. So it's going out of the system. And this is kilojoules. So going back here, we just, do this, draw work out. And yeah, this should be your final answer.